Welcome to Patrick Talks Math. Today's topic is going to be trigonometry. We're going to take a look at triangles that don't have right angles. The standard sine, cos, and tangent functions that we often use involve triangles like this one, where we have a right angle. But if we remove that right angle, we can still have a triangle, but we have to come up with a different rule to solve it, and that's why we have the sine law. The sine law involves one simple fact, which is that if I know an angle and the side that's opposite to it, then I could use that ratio to solve for anything else in this triangle. And it's all about opposites. Opposite angles and sides will always match up. Now let's take a look at an angle in general and see what kind of properties we could come up with. As I make an angle with the two markers here, notice that as I decrease the size of it, the side that's opposite, the part that connects the two caps, gets smaller. As I increase the angle, the opposite side right here also gets larger. This relationship of opposites is usually connected to the sine function in trigonometry. Sine of our angle is equal to opposite divided by hypotenuse. And that's why our sine law is going to be very uniquely connected to opposites within our triangle. Our basic sine law is a ratio, comparing angles and sides together. We could write it with the angles on top, where I compare angle divided by side, or I could rewrite that using reciprocals, where I do side divided by angle. With regards to this triangle, I'm going to label this angle right here with a capital A, and identify the side that's opposite to it also as A, but I'll use a lowercase n. As long as I can identify an angle and a side that are opposite to each other, and I have this information, I can use the sine law. So if I know this angle right here as being capital B, I can solve for the side over here, lowercase b, because they're all connected. Just to finish the diagram, we have angle C at the top, and that corresponds to side C at the bottom. So as long as I have a side and an angle that match up, and it's given to me in the problem, I can use the sine law. So let's take a look at a couple problems, one where we're solving for an angle, one where we're solving for a side. In this triangle here, I do have an angle and a side that are opposites to each other that are given to me and that I can use to solve for missing information. This 15 meters right here corresponds directly to the 40-degree angle in the bottom. This 10 meters corresponds to an unknown angle, so I'm going to use the sine law to figure this out. Since I want to solve for an angle, I'm going to use the equations so that my angles are on top. Algebraically, this just makes sense to always keep my unknown in the numerator. It's always a good idea to label our diagram, so let's label angle A and the opposite side as lowercase a. This is angle B, and the opposite side to it is lowercase b as well. Plugging this information into our equation, I can now write down that the sine of 40 degrees, which is angle A, divided by the side that it goes along with, which is the 15-meter side A, right there. And that's going to be equal to, keep our angles on top, so the sine of our missing angle, we'll put sine theta, and divide that by the side that it goes with, which is the 10-meter side. We've now set up our equation, but notice that this first part is really convenient. Setting up my equation properly gives me one side that I can solve. Sine 40 degrees divided by 15 is equal to 0.0428. And that's equal to the right-hand side, which is sine theta divided by 10. Now my goal is always to isolate that theta, that missing angle. So I'm going to multiply by 10, because that cancels out right here. And if I do it to one side, I have to do it to the other side. What I end up with is 0.428 is equal to sine theta. Now I never want sine theta. What I really want is to know what theta is. So this is the case where I'm going to use the inverse sine function of this decimal. So inverse sine of 0.428. Plugging that into the calculator is going to give me my final angle, which is 25.4 degrees. This is where I always like to check my answer and see if it makes sense. Notice I started with 40 degrees and ended up with an answer that's smaller than it. Well, 40 degrees corresponds to 15 meters for a length of the side, and my unknown angle corresponds to a smaller side length. So it makes sense that a smaller angle corresponds to a smaller side. Here's another type of problem, a little bit different than the previous one. This time I'm going to write my sine law with the side on top. Why? Because it's a side I want to find. X is a side. Let's always start by labeling our diagram, angle A and side A, opposites to each other. angle B and side B, which is my unknown side, also opposites to each other. So let's fill in our equation. Side A is 60 meters in length, and the angle that it goes with, the one that's opposite to it, is the sine of 50 degrees. Just for convenience, it might always be good to label your diagrams and indicate the opposites as well, match them up. Now, side B is x, that's our unknown, so of course that's in the numerator once again, and of course that goes along with the angle that's opposite to it, which is sine of 30 degrees. As with the first question, if we set this up properly, we can always solve this first fraction. Plugging it into a calculator, we end up with 78.3 being equal to the right-hand side, which is x divided by the sine of 30 degrees. And also like last time, I want to isolate this x, get it by itself. So let's multiply by sine 30 degrees so that these cancel out, just like last time. And if I do it to one side, I have to do it to the other side. So now let's multiply by sine 30 as well here. This leaves us with our equation to solve for x. Plugging it into the calculator, we will see that 78.3 times the sine of 30 is going to be equal to 39.2 meters. So let's compare our answer to the rest of the triangle. Notice that we had 50 degrees here that we started with, which is bigger than 30 degrees. So the 60 meters should end up being bigger than the side that corresponds with the sine of 30. And this makes sense in this case, as 39.2 is much smaller than 60. So there you have it. Remember, sine law involves triangles where we do not have 90-degree angles. As long as I have one side and one angle that match up that are given to me, if I'm given any other piece of information, I can solve for a missing side or angle. Till next time.